Okay, so 4.4 talks about determining restrictions on composite functions. So basically, the focus for 4.4 is going to be looking at the domain and range of the functions that go into the composite and then determining how that affects the domain and range of the composite function. And that's kind of a pre-calculus, like obviously this is pre-calculus, but that's a really, really direct read to calculus because you're going to have a lot of stuff to do with limits and that sort of thing when you get into calculus. So it seems weird now to focus on it maybe, but it's something that's going to lead into calculus pretty directly later on. Now, this one gives us a linear and a quadratic equation. This is example 1, actually. Guess I should have written that down. Example 1. And our first thing that they ask us for is the domain and range of each of the functions. So this is just 2x minus 1. It's a linear equation. It's y equals mx plus b. So the domain and the range are not limited because you're just going to have, well, it's 2x plus minus 1. It's going to be like a graph that looks kind of like that because it's got a slope of 2 up 2 for every 1 that it goes over, and it starts at negative 1. So that means that my x and my y are both in the realm of all real numbers because there's no limits to what x or y can be. It's just a straight line, goes on forever. If I look at this one, I've got a quadratic equation where it's simply x squared minus 2. Now, if you remember from before, if we have a minus 2 on the end, that means that it goes like that, and this is at negative 2. So I can determine that x is in the realm of all real numbers because it's just a quadratic equation and it's going to keep going in both directions for x forever. And range, because this is positive, it opens up, and because this is a negative 2, that means it starts down at negative 2. So that means that y is greater than or equal to negative 2. If you're ever in doubt, just put it in your calculator and have a look at the graph. Now this function, they ask us to graph it. And there's a few different ways we could do that. So I could use a table and I could plug in a bunch of values for x and then use the, like, put them into here and then put them into there. Or I could make the composite equation by plugging f of x into g of x, where all of that goes. So your book actually chooses to write out a table. So they use x, f of x, and g of f of x, like that. So basically they're doing the two machine system where you're going to put in some values for x, you're going to run the calculation, and then run the second calculation. So for negative 2, negative 1, 0, 1, and 2, that's a nice, well, it'll give us a good idea of what's going on here. We've got, if x is negative 2, I go 2 times negative 2 gives me negative 4 minus 1 is 5, so I'll have a negative 5 here. If this was negative 1, 2 times negative 1 is negative 2, minus 1, negative 3. And so on. I just plug that into the equation until I've got some of my numbers here. Now, I take that number and plug it into the second equation because f of x is inside and then g of x is outside. And if I plug negative 5 into there, negative 5 squared is 25, minus 2 gives me 23. So I'm just plugging it into the original equation. If I do negative 3 for the next one, that's 9 minus 2 is 7, and I continue on so that I build my table up with, and you can see here's a pattern, right? So when I graph this, I'm going to create a graph that has these values on the x-axis. So my negative 2 and my 2. And I'm just going to plot these points. Not these ones. These ones were just in the middle so that I was finding these ones, but these are my final points. So obviously 23 is going to be pretty high, but I'm just going to imply the 23. So I'm going to have a point at -1 and 7. So at -1 and 1, 2, 3, 4, 5, 6, 7 is there. And 0 and -1. And 1 and -1. 2 and 7. So you can kind of see that something's going on here, and it looks like it's going to be a quadratic equation. In fact, a quadratic pattern. In fact, if we added one more here, I go 2 times 3 is 6 minus 1 is 5, again, squared into this formula is going to give me another 23. So basically what I've got is this is probably going to go below the line here and up through there. It's a terrible drawing, but you get the idea. It's a quadratic equation. And if you really wanted to test where this end piece went, you could find a value for x that's like at a 0.5 and really narrow it down. But that's kind of beyond what I'm willing to do right now. So, the next thing they want me to do, the next thing they want us to do is to state the domain and estimate the range for this one. So I am going to use that 0.5 and get this value in here. So I'm going to throw 0.5 in here. 2 times 0.5 is 1, minus 1 is 0. So I guess we'll just add a line. I don't know if you can see this in your screen, but I'm just using the 0.5. And then 0 minus 2 becomes -2. So it looks like this dips down to -2 here. So my graph's a little out of whack. But we know that the y value is -2. So when I set my domain for this one, it looks like the domain is just x is in the realm of all real numbers because it's just a quadratic equation. And the range is that y is greater than or equal to -2 because that's where it comes to. So we did need to do a little bit of extra exploration there to find out what that would be. Now, I don't really love doing it this way because I find it a lot easier to just figure out the formula and go from there. So I'm just going to show you that one really quickly. If I did g of f of x, I'm just going to take this away now. We'll leave that. G of f of x means that I'm going to put f of x in everywhere that there is an x in the original equation, which means that I've got something squared minus 2, and inside those brackets is 2x minus 1, because that's what f of x is. So 2x minus 1 squared, now that I've got the function here, I'm just going to switch colors. 2x minus 1 squared is the same as 2x minus 1 times 2x minus 1, and then this minus 2 on the end. So I'm going to FOIL it. I'm going to go 4x squared minus 2x minus 2x plus 1 minus 2. So I end up with 4x squared minus 4x minus 1. Now, I could just plug that into my graphing calculator, and I'm going to come up with that. If I don't, then I did something wrong. I could also use the y equals a times x minus p squared plus q format just by algebraically moving this around to get that by using the vertex points and whatnot. So algebra becomes a little less cumbersome than the table idea, the input to each system, when you really think about how many steps that it takes to get it done.